Welcome back to the podcast. Today, we're diving into the intriguing and often complex world of distributed systems. These systems come with their own set of challenges, from unpredictable network delays to the various ways nodes can fail. Whether you're a seasoned engineer or just curious about the topic, there's plenty to unpack. So let's jump right in. To start, we need to understand the foundational concept of the system model. This abstraction helps us define the types of faults we might encounter. There are several models to consider, but we'll focus on two primary ones: the synchronous model and the asynchronous model. In the synchronous model, we assume that network delays and process pauses are bounded. This means we can expect some level of predictability. While everything might not be perfectly synchronized, we can count on delays not exceeding a certain limit. However, this model often falls short in real-world applications. Most of the time, we face unbounded delays and pauses, which leads us to the asynchronous model. The asynchronous model is much more reflective of the reality we experience. In this model, we can't make any timing assumptions, and algorithms can't rely on clocks or timeouts. While this model can feel restrictive, it's essential for grasping how distributed systems behave under various conditions. Now, let's consider the topic of node failures, which can occur in several ways. There are three common failure models we should be aware of. First, we have crash failures, where a node stops responding unexpectedly and doesn't come back online. Then, there are crash recovery failures, where a node crashes but can eventually recover thanks to stable storage that preserves data across crashes. Lastly, we have Byzantine failures, where nodes may behave unpredictably, sending false information or failing in unexpected ways. Among these, crash failures are often the most useful for designing distributed algorithms. So how do we determine if an algorithm is correct? This is where properties come into play. For example, in a sorting algorithm, we define correctness through properties like order, ensuring that any two distinct elements are arranged properly. In distributed systems, we need to establish similar properties that define correctness, such as uniqueness and monotonicity for fencing tokens. Let's break down the two main categories of properties: safety and liveness. Safety properties ensure that something bad never happens. If a uniqueness property is violated, we can identify the exact moment it went wrong, and that violation cannot be undone. On the flip side, liveness properties are more optimistic. They might not hold at a specific moment, but we expect them to be satisfied eventually. Much like the idea of eventual consistency. In distributed systems, it's crucial that safety properties always hold, even when failures occur. For instance, a request might only receive a response if a majority of nodes are still operational and the network has recovered from any outages. This leads us to the concept of a partially synchronous model, where we assume that eventually the system will return to a synchronous state. However, real-world implementations often complicate these theoretical models. While we might assume that stable storage survives crashes, what if data becomes corrupted or lost due to hardware errors? This unpredictability can lead to scenarios where nodes forget previously stored data, breaking quorum conditions and jeopardizing the correctness of algorithms. Let's also touch on the challenges of detecting faults in distributed systems. Most systems lack accurate mechanisms to determine whether a node has failed. Instead, they often rely on timeouts, which can't differentiate between network issues and actual node failures. This can lead to false assumptions about a node's status, especially if it's experiencing degraded performance rather than a complete failure. One defining characteristic of distributed systems is that they operate without shared memory or common knowledge. Each node is independent, communicating solely through an unreliable network. This independence means that major decisions require consensus among multiple nodes, often necessitating complex protocols to achieve agreement. For engineers used to the idealized environment of a single computer, where operations are deterministic and reliable, transitioning to the unpredictable nature of distributed systems can be quite a shift. Conversely, distributed systems engineers may find single computer problems trivial by comparison, underscoring the complexity inherent in distributed architectures. Another critical aspect we've discussed is the nature of network delays, clock synchronization, and process execution. While it's possible to achieve hard real-time guarantees and bounded delays, doing so can be costly and lead to lower resource utilization. Most non-safety critical systems choose cheaper, less reliable solutions. One of the advantages of distributed systems is their ability to run continuously, handling faults and maintenance at the node level without interrupting overall service. However, this relies heavily on proper configurations. A poorly executed rollout can still bring a distributed system to its knees. Throughout this conversation, we've highlighted a range of problems that can arise in distributed systems, including packet loss, unpredictable delays, clock discrepancies, and unexpected process pauses that can lead to nodes being misidentified as dead. The key takeaway here is that partial failures are an inherent part of distributed systems. When software interacts with other nodes, there's always the potential for failure or unexpected slowdowns. As engineers, we need to build tolerance for these faults into our software, ensuring that the system can continue functioning even when some components fail. To effectively manage faults, we must first detect them, which is no small feat. Many systems lack the necessary mechanisms for accurate failure detection and often rely on timeouts that can misinterpret network issues as node failures. Additionally, nodes can enter degraded states, complicating the troubleshooting process. In summary, distributed systems operate without a global state, shared memory, or synchronized clocks. They rely on unreliable networks for communication, which makes consensus and decision-making a complex challenge. While it can be tempting to stick with the simplicity of single computer systems, the benefits of distributed architectures often outweigh the challenges. As we wrap up this discussion, it's clear that while distributed systems present numerous challenges, they also offer powerful solutions for scalability and resilience. In our next episode, we'll delve into some of the algorithms designed to address these issues and improve the reliability of distributed systems. Thanks for tuning in, and we hope you'll join us next time.